Alright everybody, this video is specifically meant to help with number 3 on the assignment 2.2, the acceleration assignment. So the idea that we're looking at here is, okay, we understand acceleration, which most people do not struggle at all with the first part, and that's what we will do as well on this particular problem as well, which we'll set up in just a second. But how does that acceleration then relate to displacement, and how can I tackle this particular problem? It's actually pretty easy, except part B is where people really get hung up because you have to find average velocity, and our general way of finding average velocity of just taking displacement over time is not going to actually work here because we want to find displacement and we don't have it, and we also, I think we do know what the time is as well. But so let's go back, let's kind of go, we do want to find average velocity on part B, and I think on part C ultimately we want to know what the displacement is. Okay, so let's use a situation where we have somebody out running at 6 meters per second, and then something is in front of them, like, I don't know, a rock, or apparently a cloud. I don't know. There's a rock in front of them. So they want to stop. Okay, so they want to stop right before there. So we're going to say they need to stop. And let's say we measure this time and we find that they stop in 4 seconds. All right, so given. Within our given, usually have to write that, but I'm going to. We would have velocity initial is 6 meters per second. Okay, velocity final is 0 meters per second. And the amount of time is, of course, what did I just say? I think it's 4 seconds. If I didn't, that's what I'm using. Okay, and part A is find acceleration. Super easy. We just stupid plug and chug here. Do note that I am doing something slightly different than the example. I think I'm going from 6 meters per second and slowing down. They started from 0 and sped up. All the main thing is here is make sure you put the 0 in the right spot of this equation. Like for us, we actually put the 0 meters per second first and subtract 6 meters per second since it is slowing down over the course of 4 seconds. And this would be a simple acceleration of 1.5 meters per second squared. Most people, like I said, do not struggle with this particular part. It's part B and C that matters. Now, the great news is with B, it's very, very easy to do, okay? But you're going to get mad at me because I've told you not to do this in another spot, so I want to make sure and address it. How do you find the average? It's actually very easy. You take the initial, you add the final, and divide by 2, which is just 6 plus, so that's 6 meters per second, plus 0 meters per second, all over 2. The average is 3 meters per second. Now, what you want to say is, but Spainhour, you told us not to do that, specifically in the problem where you walked across the front of the room. So I want to show you kind of why it works briefly here, and then I'll finish up with a part C, which will actually be pretty darn easy to do. Okay, so in the problem where Spainhour walked across the front of the room, he walked something, I don't remember what year's numbers are, but let's say 4 meters and 4 meters. Okay, and in this section over here, he was traveling 3 meters per second, and in this one over here, he was traveling 1 meter per second. And ultimately, you actually end up finding that the average is not 3 plus 1 divided by 2 to get 2, but the average in this case is actually 1.5 meters per second. And we talked about this in class, and the idea is actually that since this one over here is taking longer, because that's going to take 4 seconds as opposed to 1.33 seconds on the first segment, there's actually more of this velocity than there is of the 3, which is why it's actually lower, and why you need to, once again, use this equation right here to get a good distribution. Okay? But how can I know not to use it in this example, the walking example, versus I can use it in the example I just said? Well, I'm going to show a graph that I think is very helpful in understanding this. Okay, if I were to graph, and I'm going to kind of try-ish to go, to scale. So 1, 2, 3. If I were to graph this situation over here, the walking situation, 2, 3, 4, 5, 6. Okay. For the first 1.33 seconds, till about that spot right there, you're going 3 meters a second. Okay? 3 meters a second. And then we say it immediately skips down to 1. And then for 4 seconds, 1, 2, 3, 4, just a little bit beyond there, you get to that third right there. you can see that we were at 1 meter per second. Now you can see from this graph that the average, if I try to take the average of 3 and 1 and say that it's 2, that's very disproportionate. There's a lot more down here than there is above. Okay? And that kind of speaks to what we said a second ago, that if there is more time, why does there not units on that? Oh, Spain. If there's 4 seconds of time on this one, there are more of this 1 meter per second, and that's why it's closer to 1.5, and we have to use that other equation. When we come back to our example over here, here we started at 1, 2, 3, 4, 5, 6 meters per second, and end at 0 over the course of 1, 2, 3, 4 seconds. 4 seconds. I believe it was 4 seconds. Yes. Okay. So now if you track this, what we say in this class is that the acceleration is changing over time, so it's pretty steady. At halfway through, and you can see that, by the way, right here. It's going down by 1.5 meters per second every second. So after 1 second, gone down 1.5. After 2 seconds, it's gone down 3, 1.5 and 1.5. After 3 seconds, that'd be 1.5, 1.5. It's gone down 4.5 for a total of 1.5 right there. And then finally we end right here at 0 for, 3 sections of 1.5 meters per second. Negative 1.5, and another negative 1.5. Oops. Sorry, my apologies. Negative 1.5 and change. So it would be at 6, then it's at 4.5, then it's at 3, then it's at 1.5, and then it's at 0. Again, units on all these, but now we're just wasting time. Okay, now if you go and look here at my average of 6 in there, here's what you will notice. An even amount of time is spent below as above over here. So what that means is that I will cover more distance over in this section because I'm going faster than the average. But over here, I'm going to lose this section. Let's go ahead and use another color. I'm not going to cover that distance. And if you'll notice, this extra that I covered in the first part is enough to make up for this section right here that I missed. Or let's try something else in case it helps. I'm going to cover the exact same distance if I go from 6 to 0 as if I just stayed at 3 the whole time. Whole 1, 2, 3, 4 seconds. Okay. So to that end, step back over here. Oops, get rid of that. Okay. Say, okay, Spainhour, then how do I do part C? Well, you'll notice earlier I said that we could not use this equation to find average velocity because we did not have displacement. But we don't have displacement here, but we do now have average velocity, and we do now have time, which is just a quick algebra to get displacement equals average velocity over time. My average velocity is 3 meters per second, multiplied by that 4 seconds, and I should cover 12 meters during that time. So the actual work of this is pretty easy, right? To review real quick. We can use our basic acceleration equation for part A, which probably none of you struggled with. We can use the general definition of average of, hey, add them all up and divide by however many there are here, 6 plus 3 to get 3. And then we can go ahead and use just our average velocity equation again in order to get displacement using our average velocity of 3 that we got on part B. The real trick the real work of this problem is understanding why the heck we can use one in one case and not in the other. And once again, real quickly, that was because in the walking example, I could not use 3 plus 1 to get 2 because they took different amounts of time at either, so this one should be more heavily weighted. Whereas in my second example right here, I spend an equal amount of time above 3 as I do below 3, so they can be evenly weighted in that particular instance. And that's how you do.